I would like to thank the organizers for inviting me here. It's an honor to me, and I congratulate you already. After the first day, you do really a very good job in organizing that. And I think it's very good practice as a young scientist to do that. There are so many little details to be considered. So thank you again for this event. Yes, the topic I was asked to talk about is how short pulse lasers can serve to move into the world of nanotechnology, which is a topic very well known to you and has become quite important, but still I think in production and everyday life it's only related to powders or sun creams and so on. So I think there's a lot to do still in research and development. Before I go into the topic, I may take the freedom to talk a little about my own relationships a little to the area here at the East Sea, because we will see that my family actually migrated a couple of centuries ago, and the University of Vienna. Just a short introduction, what are the major features of our university in Austria. So there will be related results which have been achieved in collaborations with the University of Natural Resources and Life Sciences in Vienna. BOKU is the abbreviation from a German word. Then the Weizmann Institute of Science and the University of Graz in Styria, and a computational center. So I come from Austria, and if you go back more or less 2,000 years ago, you see this dot here was called the Kingdom of Noricum. And this Kingdom of Noricum was a Celtic kingdom, and they had a lot of troubles with German tribes always attacking from the north across the Danube. So they decided we join NATO and they take care of it. So they joined the Roman Empire around the birth of Christ, and it became a Provincia Norica. It's the only province of the Roman Empire in the north which did not fight against the Romans and joined. It's interesting. So they rather gave their daughters for marriage into Rome before, and then the Habsburgs did later on, you may remember. Okay, so Vienna is just at the edge of this province. And if you look at that, we are located here. Vindobona was the name, and then came Carnuntum. Actually, the Amber Road from the East Sea crossed the Danube here, just east of Vienna, to go to Aquileia, to the Mediterranean Sea. A very, very important road for more than 3,000 years, I would say. Okay, so you had a lot of attacks here across the Danube, and the Marcomanni and Quadi were there. These are German tribes that you see your area, probably about there. It's quite interesting, 2,000 years ago. Anyway, the Romans built at the Danube, you're looking here west, a military castle, which is the center of Vienna today, and they moved the Celtic population from the mountain Leopoldsberg, yeah, which was a Celtic oppidum, a city on the mountain, and moved them down into a civic city next to the military camp. And then, of course, very important, they built the Limes Road. And our chemistry department is just at the Limes Road. Yeah? So we are looking out of the window, and this road is one of the most important roads of the Roman Empire in the north, to move troops and military, but also trade and economy and people. Anyway, outside the city, the Limes looked like this. People think so, okay? Stretching from the Rhine River all the way back to the Black Sea. And then our population is quite a mixture, because we know that from all kinds of places, from the Roman Empire, officials and military soldiers and so had moved to Vienna, and then they retired, they married, had children, so the population is quite mixed. So actually, well, now let's have a short look. I'm sorry that I'm not going directly into physics, but actually Vilnius is here, and the history is quite mixed, as you know, from your background. And the Battle of Grunwald somehow affected the fate of my family, and you will see why. Because the Teutonic Order, of course, was occupying this territory, as you know. And then there was the battle here at Grunwald. And part of this then went to Polonia, and you were fighting together with Poland at that time. It was an allegiance, I know, and probably your soldiers looked like this, I saw. And so a part of this country became Polish here, yeah, under Polish ground. And so my family lived there in a little town, Rösel in German, Rösel, near Eilenstein. And what they did there, they were administering a castle, a Teutonic castle, formerly Teutonic castle, this Rösel castle, and for a couple of generations. And all of a sudden, they disappeared there. And what was the all of a sudden? Well, you know, the First Polish Division, when the powers of Prussia and Austria and Russia started to absorb Poland. So what happened to my ancestors? There were high officials reporting to the Bishop of Eilenstein, and he reported to the King of Poland. They were Catholic, and the Prussians came, so they lost their existence, and they had to go. So where do you go if you're Catholic and you lose your existence? You go to Austria. So what they did, they went to Austria, from there into Western Bohemia, which was German-speaking at that time, and in 19th century, finally ended up in Vienna. So that's my fate, a little background, how my family comes from the East Sea area into Vienna, and that was the result. Okay, so far. Now let's move to my university, which may be more interesting to you. The University of Vienna is the oldest German-speaking university still existing. The oldest German university was Prague. It was founded by Charles IV, yeah, the famous King Charles IV, a Luxembourg family descendant. And he had a son-in-law. And this son-in-law was Duke Rudolf from Habsburg. This is one of the first portraits in European history, interestingly. Very funny face. But he founded the university in 1365. His father-in-law founded it, I think, in 1348. That was Prague. It's not the first university in Europe. The Jagiellonian in Krakow is older, Paris is older, Bologna is older, and so on. Anyway, he was very careful. He was negotiating with his father-in-law because he wanted to compete with him, but he didn't want to annoy him. So he founded that, and unfortunately, in 65, in his 26th age, he died. But he was a very active young man, very active young man. So today, this is the main building from 19th century of our university. If you have been in Vienna, you may know it. Well, physical-chemical tradition in the University of Vienna. Let's come to a more concise point. You may remember those names. There have been teachers at our university, Christian Doppler. Okay? So then Johann Josef Loschmidt, he was also teaching at our university. Ludwig Boltzmann was a professor there. Ernst Mach was a professor there. Our von Welsbach, you may not know so closely, so I will have another transparency for him. Erwin Schrödinger was there after Second World War. During Second World War and before, he joined Trinity College in Dublin, in Ireland. And Hermann Mark, you may not know him if you're not a chemist. Hermann Mark was the inventor of polymer chemistry. He actually, because he was Jewish, he had to leave to United States from our department, actually, and he founded polymer chemistry at DuPont in Maryland, and then returned. He was with IG Farben before in Germany, and then he was teaching polymer chemistry, and so it's also remarkable for our everyday life. Well, our von Welsbach, that's in front of our chemistry building. he's the inventor of the bulb based on a metal wire. The inventor of the bulb was actually Edison in Boston, okay, with carbon wires. But the carbon wires, of course, they didn't live very long. Maybe a couple of days, then boop, the bulb was gone. So he invented the wire based on osmium and tungsten. And you know the name of osmium and tungsten in German is Osmium und Wolfram. So he invented the acronym OSRAM, and still existing brand. Interestingly, he filed the patent in Berlin and not in Vienna. I don't know why. So anyway, I think it also changed the world. Now we are at the verge of completely change of lighting fixtures. You know, we will have a technological change and it will improve our world. Now, laser applications. Where do we have lasers? Before I come to the short pulses, you know, laser shows. You know, all these products, which all have been cut by lasers. Even the keyboards here, the keyboards in our computers are written with laser beams. And you also know these souvenirs in a bulk glass, which is very interesting. How does the picture come into it? Actually, it's in the focus of a laser spot, and you change the refractive index there, at least that. So it works very cheap and quick. Well, this is annoying, you know. Our police is playing around with the Doppler principle to quantify our speed. You may have experienced that. And also you can measure distances in space and to the moon and so on. A standard technology is welding by lasers, and all over the world you can be sure cars are now fully automatically welded. Robots, and at the end of the robot arm you will have the outlet of a fiber which delivers the laser beam. So this is an old picture, as you can see. This is maybe 20 years ago, almost, an old Golf Volkswagen. Well, there are also very high power applications, very unique. This is an airborne laser. It's a little funny, but it exists. It exists. The laser, the power generation, then the laser, and at the front you have a nose-mounted turret to direct a laser beam to a target. That's the laser on board. Yeah? So that airplane exists, I think, only once in the world. And I have also pictures that the Soviet Union started doing this, and they have also one airplane for that, but they don't produce it anymore. Anyway, they tried to destroy targets air-to-air, but there are also other fixtures, ground-air, like Northrop Grumman developed, for instance, such a Nautilus tactical high-energy laser. It should work to intercept a missile, and they showed, and you have, of course, countermeasures. If you turn the rocket, and of course the target doesn't get so warm, and so on. So maybe it's not very perfect, but that's the people are thinking, and then also a Humvee-based laser. So this is a little curiosity, but lasers are in many, many parts. What is a laser? You are scientists, I don't have to repeat. Well, it has to do something with this instrument. Yeah? You are pumping water into some level, yeah? And it waits there. And we call it inversion, you know, inversion, higher population up there, and then you decide you trigger, okay? So, stimulated emission, and then you have radiation emission, and if you do the right optics, I will show you, then you can laze, as we say. Well, the laser light has a certain property, very important. The thermal emitter emits photons in all directions, like this here, and the laser is collinear, and you see the same phase, and so on. Well, it's a very simple thing. You have this laser medium, which can be pumped, yeah? And then you need just two mirrors, 100% reflectivity and less than 100. And then you just harvest this outcoming laser beam. That's actually the basis of lasers. And this laser light can be very strong, highly intensive. So we let it interact with matter. Very simple. There's an electron between a couple of atoms. It interacts, and the electron will answer, yeah, more or less resonantly or not. And the electric field from the light will cause it to move. And the answer at the stiffness of the electron, we actually measure with the index of refraction. Okay, you remember that. And if you do it too much, then the solid may disintegrate, ionize, or disintegrate. So these are the follow-up processes. There's another parameter which is very important, is the wavelength of light. Very simple, in a linear world, if you have long wavelengths, the penetration depth is long, Lambert-Beer law, you remember. And if you have a medium wavelengths, then you have a very narrow absorptivity and a very shallow absorptivity in the UV. So the results of interaction are very different. There you have more melting, vaporization. Here you have shocks. And here you're actually breaking bonds if you have polymers or organic material or tissues and so on. So you can play with this. But you can also play, of course, with the length of the pulses, and that will be the topic of the rest of the talk. First, we want to go into the nano-world. So you see, we are in the world of viruses, bacteria, viruses, and nucleic acids, and so on. So that's the nanoscale. And if you go into the femto world, then you see we come to the femto with this number of zeros behind the comma, just at the edge between the fastest chips and electronic motion in matter. Okay, well, to give you an impression, you know, in 1 second, light circumvents 7.5 times the globe, and with 100 femtosecond, yeah, 10 to the minus 13 seconds, light just travels 70 micrometers. And that's half the diameter of a human hair. Okay? That's the distance. And in 5 seconds, which for instance, near infrared light is the shortest pulse you can get, you only have 2 cycles of an electromagnetic wave. Shorter you cannot go, because then you have no wave anymore. Okay? So these are some features which may be interesting. Now, interaction. And you will see, I will come back always at the terms thermal and non-thermal. Well, this is just a Mickey Mouse picture to show you if you have long pulses, then you have a long-lasting interaction of the laser light, and therefore heat, which is dissipated there, can travel, diffuse into the solid, as you can see. And you will get the heat-affected zone with all the problems of melting, deforming, splashing, and so on. And if you go to the short pulses, then you're reducing these zones and side reactions. Just for the beginning, let's leave it that way. So there is a chance to be very precise. The applications where you have to be precise and where you want to avoid collateral damages, yeah, are, for instance, in mechanical engineering. These have been examples more than 15 years ago in the German project with Bosch. The company Bosch is developing injection systems for combustion engines, you know, and they have to have very small openings, and they are drilling these openings up to nowadays with mechanical drillers with a diameter of 100 micrometers. And the engineers would like to have oblique angles, but you can never mechanically drill that. Yeah? So a laser can do that. So that was one part of the project, to drill holes into injection pump discs. Or in neurosurgery, you want only to cut one nerve and not the collateral tissue. So that is a chance in neurosurgery. Then also dentists got interested because they want to reduce the pain in drilling of teeth. So that's one possibility. And really a real application, which is now done thousands of times all over the world, is using a femtosecond in cutting slices on a human cornea in the human eye. And I can say this is the application of nonlinear optics. It's a wonderful thing, and it works. Good. So nowadays, such laboratories like ours are very, very concentrated and small. And when I started 20 years ago with femtoseconds, I had to fill a huge laboratory with pump lasers and so on. So that changed. Now, time scale, okay, microseconds, nanoseconds, pico, femto. And now we are looking at the electronic system and the atomic system in the course of time after interaction with electromagnetic light. So the absorption of photons is in the beginning, and it's certainly faster than, I would say, faster than 10 or 1 femtoseconds. In the meantime, people are working with attoseconds and looking at the fate of electrons between orbitals. Now, then we have a phenomenon called the impact ionization, then the carrier-carrier scattering, and at the end, the electrons dissipate their energy to the lattice, and that's called the carrier-phonon scattering. And that's the end of a domain which we call non-thermal interaction. The electrons are hot, the lattice is cold, the lattice doesn't know that there are hot electrons yet. Okay? Afterwards, you have a bunch of processes, quite complicated, the carrier removal, Auger, radiative recombination, carrier diffusion, and then material move, ablation, evaporation, thermal diffusion, and that's the end of the story, and that's what the engineer needs, the resolidification product. That's how the workpiece looks like. Yeah? So that's the border between the non-thermal and the thermal processes. It's a couple of picoseconds, Therefore, if you want to use that domain, you have to pulse shorter than 10 picoseconds or 1 picosecond. Good. Now, I want to give you a short glances into this world of metals, dielectrics, and then at the nano patterning. First, the metals, very, very short. You have excitation in the metal above the Fermi level. And at the end, you have first a free electron scattering, Maxwellization, and then a phonon emission, and then the material is hot. That's quite simple, but there is a time delay of this between non-thermal and thermal. So that's another picture. Here's the electronic system, and here's the lattice symbolized. So your start here is the Fermi level, the energy, the population, and you are tearing out the electrons when you excite. The lattice doesn't know that at short time. Then after the scattering of free electrons, you have a distribution. So the distribution function is spread around the Fermi level. Electrons, the lattice is still cold. And then at the electron phonon relaxation time of a couple of picoseconds, the lattice is hot and the electrons are in equilibrium with the lattice. So that's what we are playing with at short pulses. There are the balances between the electrons here. This is the capacity, heat capacity, diffusion term, the generation term, and the dissipation term. This dissipation G here is the generation term for the lattice heating. Yeah? What the electrons are dissipating to the lattice is the generation term in the lattice balance. Now that's the so-called two-temperature model, and to a first-order approximation, this is a very dependable approach to describe the interaction of ultra-short pulses with metals. And here is the border between non-thermal and thermal, and then in the long run you can describe it with the classical heat diffusion equation. There are wonderful calculations by Leonid Zigilai. For instance, at lower temperature you see here time. Here is the temperature and here's the pressure. And you have an expansion, of course, of the material, melting, yeah, crystal, liquid. And what is very interesting, you have a rarefaction, so you have underpressures. And this underpressure here may tear apart the material and end up in bubbles. And there's a big discussion going on that in materials which were not evaporated, you're creating nanobubbles in the bulk, which changes the physical properties of metals drastically. But this is still under discussion. If you increase the temperature, the energy of the laser, then of course you are disintegrating the material, and you see that hot splashes are coming out of the material at a certain pressure. So that's how people discuss these things in recent years. You see, that's quite recent. Now, that was the metal. And metal micro machining is difficult because the metal makes splashes, as you say. Yeah? As you see, these splashes is a problem in machining. Well, the dielectric is something different. The dielectric normally is highly transparent to light, and therefore it should not interact at all. But if we are applying nonlinear optics, multiphoton excitation, or, and you will see also another process, which is called the Avalanche Excitation, there you need thermal electrons which are present due to defects. And the defects, I don't have transparency for that. Remember, a crystal, a classical crystal, and a normal material in engineering is so different because normal materials are highly deficient. They have many defects, and the defects can inject electrons into the conduction band of dielectrics, and then you have some conductivity there. And that is also important for excitation. So, come back to an experiment which drew us to a lot of clues. You have the pulse duration, and the pulse duration is nothing else. If you go shorter pulses at constant energy, the intensity of the peak is increasing, yeah? The power. So, shortening the pulse means you can reach at low energies a high intensity. Now, here on the y-axis, there is the threshold fluence. What means the threshold? For a conversion of the material. In that case, it was the evaporation of a dielectric. The evaporation. So you see here, in this domain, above the picosecond range here, this follows a classical diffusional model. Why? Because the heat is dissipating, yeah, and therefore you're losing the energy for evaporation. So at longer pulses, the intensity is low, so you're losing the energy into the bulk of the material. And that goes all the way down to the time where the electron phonon relaxation time takes place. Well, and below that, nothing should happen, because then the material just gets hot after the electron phonon relaxation time. But what we observed, we still had a reduction of the fluence, the threshold fluence. And that we didn't understand at that time. And then we did another experiment. We looked at the quality. Look, for instance, that is a fused silica ablation, 3 picoseconds. It looks quite bad. There are a lot of splintering and so on. If we shorten the time or increase the intensity, then at 220 femtosecond, it got a little better. That was state of the art for decades, you know, in femtosecond, hundreds of femtosecond. Then we shortened to 20 femtosecond and it improved. And then we went to the shortest pulse possible, yeah, and it was better even. So by increasing the intensity, we could change below the time of electron phonon relaxation. We could improve the quality. We didn't understand that. Now, a short explanation comes in this picture. Remember, we had these processes in the metal, just scattering of free electrons and then heat dissipation. Now, in dielectrics, it's more complicated. in dielectrics, we have the choice between a multi-photon excitation, otherwise we cannot couple light into it, or we have the impact ionization, then we have the free carrier absorption, if we have free carriers, but we have to generate them first. Then we have Auger decay, we have the classical recombination, like you know from semiconductors, solar cells, and so on. And then you have the free scattering, and then the phonon emission. So, what process helps us to interact with the dielectric? Here, I would like to sum up with the help of Mr. Stoyan in France. Here is the number, the rate of generation of free electrons. And if we have too many free electrons, then the material may disintegrate. So that's the measure. And that a positive contribution is the multi-photon excitation, short times. We have another possibility if we have defects, as I told you. They generate a couple of thermal electrons in the conduction band, and they can serve an avalanche process together with the free electron absorption. And then we have losses. One loss is, of course, the inelastic electron-electron scattering, and then finally the electron-phonon scattering, which heats the lattice. So when we increase this term here, we increase a deterministic excitation process. Deterministic. And remember, the best result in ablation of a dielectric was at highest intensities. So the multi-photon excitation is a deterministic process. You can determine the result, the excitation. If you go to longer pulses and lower intensities, then you have to make use of stochastic processes. You have to reckon with free electrons, which are there due to defects, and sometimes it works and sometimes not, and the avalanche process is stochastic, it's not deterministic. Sometimes you have an explosion, sometimes not, you know. So therefore, you remember the results were quite bad, the ablation. So we can switch between stochastic and deterministic processes. Remember, the multi-photon process is a deterministic process, and if you do, for instance, multi-photon excitation of polymers, it's deterministic. Nice results. Huh? Finally, non-thermal material patterning. Why is it interesting to have a surface with nanostructures? So we call them also the periodic nanostructures. Well, self-cleaning surfaces are interesting. You all know the Lotus effect, self-cleaning surfaces. You may be able to produce them artificially. Then in tribology, this is important. In the meantime, the people could prove that even nanostructures at a surface can improve the tribology and reduce the friction strongly. Yeah? Then holographic design elements can be introduced. There are companies who are selling that already for security reasons. Then you have diffractive security features like this, but also there. Then the field amplification at surface structures. That may also be interesting. If you want to produce, for instance, electron-emitting electrodes for certain instrumentations. And finally, cell growth engineering. So cells are very, very sensitive where they grow and what substrates. And you can even trigger higher growth rates, or you can also direct and control the direction of growth of cells. So that is also an application. Now we have two possibilities with the laser to produce periodic structures at the surface. First, we have the so-called static model. We modulate the energy input. We need an interference of the light, and then we get interference patterns. Classical. I will show you also that, and you can go into the nano-world even though you may have not too short wavelengths. And there are masters of this technology here. I understand you are doing that also, but also there are people who are concentrating on that in laser laboratory in Göttingen in Germany. The dynamic model is completely different, the second one. You just excite the material, and then we come into this non-thermal phenomenology, as you remember, and we'll show you. And then the material organizes itself. It's a self-organization-based process. And then you form that. I tell you, the mechanism is not completely understood until now. There's a lot of discussion going on still. Well, the static technique, interference in a Schwarzschild objective, for instance, you can make very nice samples of interference. Or you control the phase, phase-controlled multiple beam interference. Then you can also use gratings with interference, grating interferometry, and that also allows you to shift a little spots, and therefore you can get into very small features. Mr. Schimann in the laser laboratory in Göttingen is a master of this, and so this is something which is really reliable. You can make very nice small features, theory, you know, and even the experiment is following that nicely. You can get features which are really in the nanometer range. It's impressive. Mr. Schimann was giving this presentation last week in Maltendorf at the conference of Femtosecond lasers in material science. He just presented these pictures. Well, now let's go to the dynamic way, the self-organization. Well, we observed when we look at a semiconductor like silicon underneath a sheet of titanium nitride, we got these stochastic features coming out of the silicon. And if we looked closely at certain energies, we saw that in an ablation grater, these periodic nanostructures changed abruptly between two domains of energy, high energy, low energy. And if you walk along the beach, you will find the same features. If the wind energy is high, then you will get such feature, and always abruptly you have small ripples. There are models for the sand. Yeah? There are models for the sand, but the models are quite restricted for laser interaction. Anyway, another feature which is very interesting is that the polarization of light is very important. You can turn the orientation by the polarization of light. Remember, we are exciting with femtosecond lasers, and the electrons are hot for a long time, then they dissipate, and the ripples are not there yet. And the ripple formation, the meta movement of atoms, takes much longer. So somehow the materials has the memory of the polarization. It's dark. There is no light anymore, but the ripples are oriented. It's very interesting. So there's a nonlinear correlation of periodicity with energy, as you can see. And as the ripples grow, nonlinear effects become important. And we also have a phenomenon which you could call bifurcation. Bifurcation. So that's not interference pattern. This is typical for self-organization, and you find that also there. How can you trigger a solid material to be able to form these ripples? You have to destabilize somehow. Well, in a non-thermal domain, you can imagine like this. This is the lattice. The photons come in. They interact with the electronic system. They excite a lot of electrons. yeah? A lot of electrons. And that changes the potential surface, yeah? The wave function, the probability to exist, and the bonding strength of the material strongly, so it gets softer. It's a softening. The viscosity decreases. And then it freezes again. It returns. So it's not a classical vibrational heating. It's just a softening and then resolidifying. That's the non-thermal melting, we call it, the non-thermal melting. You can prove that in an online setup. For instance, you take a laser beam, a strong laser beam, excite X-rays, yeah? Use this X-ray source to probe the sample, and at the same time, with a time delay, you're using an optical excitation. That's the experiment I just showed you in this Mickey Mouse picture. And you see online as that the material softens. Okay? There are such results, yeah, that the intensity of a peak or the broadness changes. So there is a softening of a lattice, and you can understand that if you plot, for instance, the potential energy of a single atom, so to say, and before and after the excitation, the non-thermal melting, you have a broadening, and of course the distribution of displacements of atoms is widening. So the atoms have a more possibility to move and then freeze again. You can calculate it also like this. We did experiments, and Mr. Garcia, he calculated and could show that a silicon lattice that actually is a little softening and then freezing again. If you overdo it, then of course it vaporizes. So that was this molecular dynamics simulation, and it proved that non-thermal melting is possible, and you can calculate the time-dependent potential energy surface, and it shows that the atoms move apart and have more freedom to exist. So there is massive instability and a perturbation of interatomic bonds. Now these ripples, you see, that's a typical observation by Mr. Reif in Cottbus. So you have small ripples, larger ripples, and a lot of features. Bifurcations, you can see nanodots, you see bead strings, they call it, growing columns, the web-like patterns, flowers, all kinds of nanostructures. There are two parameters which control that. The shape and orientation is controlled, as I told you, by the polarization. It's a very miraculous thing still. And the irradiation dose, the energy density, the periodicity, interestingly, and the feature size. Okay? Remember, we already had the picture. We are looking at this here. So self-organization has to be understood. The static interference model, classical, the periodicity, the lambda, capital letter lambda, is proportional to the wavelengths of the light, you know. Classical optics. Coherence is necessary. In the dynamic self-organization model, the periodicity depends on the deposited energy. The deposited energy and the number of pulses. And people don't understand really. There is a trial to understand. A model of roughening plays with the surface tension and the extent of roughening age in this case. Yeah? So it's a competition between roughening and smoothing because of the surface tension. So surface energy is certainly very important, and we have surface tension, that's chemistry. Bond strengths at the surface, presence of ligands, presence of coatings, and so on. So we have to play with this to understand. We may resort to the Kuramoto-Shivanshinsky equation, which gives you the roughening as a function of surface tension and dissipation. So surface diffusion is important, and that's an activated process. And just to show you that the ripple wavelengths, the periodicity, is a function of the activation energy of the diffusion. And in a simple model Mr. Reif was calculating recently, he could show if you decrease the activation energy in the metal, it's very easy to move and very tough to move in a dielectric, you see such a situation which is quite nicely showing the real world. So there is a way a little to understand. But really how you disintegrate the material and destabilize, it's still an open question. You can play with a delay in a pulse shaper as we did, and you can show that you can influence the size also by shaping the pulse, and you can disintegrate the ripples when you are beyond the electron phonon relaxation time. So there are a lot of data present now. At the end, let me come to a quite interesting top-down and not bottom-up structuring process, the apertureless femtosecond SNOM scanning nonlinear optical microscopy. You have an atomic force microscope tip, and you excite the tip with a laser, femtosecond laser, and you're playing with the plasmon at the tip. So the motivation is, of course, to come around the problem of Mr. Abbe. The ability of resolution is limited by the wavelengths and the aperture in the denominator. So if you want to become finer, you have to play a trick on nature. And the trick on nature is based, in our case, on surface plasmon resonance effects. Then on the tip, you have a lightning rod effect, yeah? Small radius with high confinement. And the antenna effect is when there is a resonance, a constructive interference possible. And that depends on angles and material and so on. But you can expect enhancement factors at the tip of 10 to the 6. And that is nice to be used, for instance, in optical nanolithography. Others use it in tip-enhanced Raman scattering, you know. Tip-enhanced fluorescence microscopy, it's very challenging. We would like to do it, but we didn't do it yet. Anyway, such a setup looks like this. You have an amplified system, for instance, and you excite the tip. Or you have a strong oscillator, as we do in Vienna. We do the same. So these are the setups we are exciting like this. Only the aligning procedures are very tricky, of course, because you have not a substrate, but you are in free space. Yeah. Okay, now, such a cantilever is a fragile thing. You can imagine if you heat the tip, at the end everything is heat. It will dissipate the heat, yeah, and it will extend in one direction, the cantilever of the atomic force, and it will also bend down because there is a metal mirror on the back for the reflection of the laser light, for positioning, you know. So it will do this, and we were calculating and showed that it's the case, and actually we could also show an experiment. It does like this. So importantly, if you want to avoid that, you have to work at equilibrium, thermal equilibrium. And then we also calculated the density of the field at the tip, yeah, by the boundary element method. Our colleagues in Graz did that, and I don't want to go in all the details, but it can be read. So we could calculate the field in presence of a substrate. This was not done before, with a gold-coated tip and a silicon tip with a curvature of 10 nanometers. Now, and then what's very important is in that business is, do you heat the surface and then scratch? Everybody can do that. Or is it a field which influences the substrate? And if that's the case, then of course, the polarization angle of excitation of the tip should have an influence. And we calculated that, and we could show experimentally, yes, there is an influence of the polarization field. Yeah? Okay. Also, the coating thickness has an influence, and the wavelength has an influence, and we are not at optimum yet, so we would like to have an optical parametric amplifier, but we don't have the money at the moment, so it can be improved. But first results show that we get melting if we have a contact mode. Tip is hot, then you have melting of the surface. Clear, simple. If you have a semi-contact mode, you know also, yeah, then there is no heat dissipation and we get nanostructures at the surface. It works, even high repetition rate laser. And in a low repetition rate laser, again, even in the contact mode, we do not get melting structures. So these are our first results on this. And of course, always the question is, do we scratch? Do we have field influence? Yes, there we can change that by the distance and the contact time and so on. And also the polarization, again, polarization of the tip P or S, P or S. The P should work. The S should be a broad distribution of energy. That's the calculation. P polarized, S polarized, you know, a broad distribution of field. Well, the results are not so clear as we would expect from the calculation. So there's still a lot to be understood. Summing up, so this is a deterministic top-down approach, excitation of a tip, and the field enhancement could be seen in polarization experiments. The outlook, we would like, for instance, to do tip-enhanced fluorescence microscopy. So if you have fluorophores on the surface, like for instance a protein in a membrane which wants to cross between membrane compartments, rafts, you could follow that and such things. That's our dream. Or optical nanolithography as a tool for graphene processing. You may have graphene sheets when we try to do that. You can weld maybe graphene sheets. You can cut, yeah, and so on. So that's an approach to do that. Summing up the activities in our laboratory. Yeah? I showed you some in the far field and near field application with ultrashort pulses. We are still also active in laser medicine, particularly in ophthalmology. And it's also an interest, lasers in cultural heritage. We have a long time experience in cleaning of organic materials. Fibers, paper, parchment, which is old skin. We are looking into polymers now. In modern arts, the artists are using all kinds of polymers and paper and paintings, and nobody knows how to clean that maybe in the future. So we are interested also in this. We are doing also hot electron electrochemistry. We will I have a poster with me out there today, and we are doing electrochemistry of proteins at non-organic interfaces. So this is the spectrum of the activity in our working group. That's the building in Boltzmanngasse. So if anybody wants to Vienna, you are welcome to stop by. And if you want not only to stop by, maybe to work with us, we have the chance now. We have a doctoral position open by the university in the group, and the spectrum of activities can be brought if you're interested. So talk to me, or you can also submit, but this is a little flexible. You can also submit to the Job Center, University of Vienna, ACAT. So thank you for your attention, and I hope I was not too long, but we have a little spare time, I understand, this morning. Thank you very much.
Okay, so thank you, the lecturer, for a really nice and informative presentation, and now we are ready to have some questions and answers. Please go ahead.
I want to ask about the self-organization. Since it's not thermal effect, it's known in chemistry that gradients across the surface could induce these structures. So is it somehow a quantum mechanical effect that you have strange structure, change in wave function due to confinement of excitation, that later these hot electrons somehow transfer the energy to the lattice?
we think we can understand that the electron density is influencing the work function. Yeah, so the wave function, sorry, the wave function. So certainly, if you correlate that and you iteratively calculate that, then you will find that the box of the electron will change. Yeah, because that's not the classical picture we learn in the first quantum mechanical lecture. Yeah, it is the box size is constant, whatever population you fill in. But there is a possibility that the box is influenced. Maybe that's a simple explanation. The box is influenced by the population, or the inversion, you know, of the population and so on.
Just as you mentioned in non-thermal material effects, the determinism of excitation is very important. Do you can comment the role of the wavelengths, say, in this determinism, or just are there some data about the role of the laser wavelengths to do it better?
Yeah. Well, we know that the probability of a higher order excitation increases with lower order. So a 2-photon process is much more probable than a 3. So clear, if we shorten the wavelengths in a dielectric, if we shorten the wavelengths, the probability for deterministic excitation increases. So that would be my answer. So at the moment we work with 800 nanometer in titanium sapphire. In fiber lasers we're even a little longer, beyond the micrometer. So it would be advantageous to have shorter wavelengths, to double, start with 400 nanometers. And yeah, people observe, it's good. But multiphoton is, I think that's very important to remember, is a guarantee for deterministic interaction. And all the other, the avalanche processes, which also possibly nanoseconds, where the souvenirs, you know, they are cheap, yeah? But it's always an avalanche and chaotic process. Yeah.
Some more questions? Otherwise, I will give my own. So one will be personal, the other will be quite specific. The personal is, from your point of view, what are the next advantages of femtosecond lasers or ultra-short pulse lasers to be implemented in everyday life, in industry? What are the limiting factors right now?
Yeah.
How long do you need to wait for some of your presented?
Yeah. Well, one of the major advantages of femtosecond lasers is you can interact in a 3-dimensional space in a dielectric. Which is not the case in linear processes. In the linear process, you have absorption at the surface, and because of Lambert-Baer, you have a reduction of interaction in the bulk. But when you can penetrate any dielectric, you can determine the spot, the focus, where you have nonlinear interaction. And that's the basis for ophthalmology. So that is certainly, it's a winning property. Secondly, the time of interaction, you can go below the electron phonon relaxation time, and therefore the collateral damage is minimum. Not zero, but minimum. So in all kinds of applications where you want that, it's good. Collateral damage, for instance, in scribing solar cell panels, or in correcting flat panel displays, and the flat panel displays get larger and larger. Now I come to the limit of such a process, and we are very interested at the moment because the scan rate or the repetition rate is limited, has been limited by 20 years, 100 kilohertz. Some people 10 kilohertz amplified systems. Well, there was put millions of euros in a German project. I was also involved to increase the repetition rate. So there was the disc laser developed in Stuttgart and costed a lot of money. They sell it, yeah? And they make 100 kilohertz. It's not enough for productivity. So it sounds trivial, but the productivity of these lasers is too low. In a single beam function. So we come from the other side. We have an oscillator, and it was the first oscillator with a long distance, with a high power. And the idea came from a group with Ferenc Krauss, who's now in Munich, and Femtolasers in Vienna, which was bought by Newport a couple of weeks ago. So we will hope that they can function in the future under American rule. We'll see. Anyway, the high repetition rate, and then you need fast scanners. And this mechanics is also not available. Fast scanners are not appropriate for megahertz repetition rate. So there are engineering problems. And then also maybe the dependability, the switch on, switch off characteristics. We are collaborating with Baltuska at the University of Technology in Vienna in developing, my postdoc is collaborating strongly in fiber laser development. Yeah? High power, shorter pulses, high intensity. Maybe that's the direction. And medicine, flat panel displays, maybe in the future, lightning fixtures, structuring lightning fixtures, photovoltaics, organic photovoltaics. Maybe there are fields where we need it.
Okay, thank you. And the next one would be more specific, like you coming out from your talk, from the second part, was about ripples in dielectrics, and as polymers are dielectrics as well, do you experience any ripples in polymers? Not in glasses, mostly.
When I did the ripples back in Berlin, we always thought interference patterns, and then we saw the nano ripples. And we took ceramics, a ceramic alloy, where colleagues of ours worked in Berlin for ceramic combustion engines, you know, without lubrication. They don't work. Anyway. And we had 3 grains of different chemistry, and then we saw that only one phase was forming the nanoripples and the others did not. So that was the first aha effect, and said, oh, chemistry is probably so important in the self-organization. Well, of course, chemistry. Yeah? So the bonding strength, we compared the bonding strengths, and we said, oh, yes, if we have a high bonding strength material, the ripple formation is accelerated. So obviously, there has to be a thermodynamic relaxation gain for the material. So if the material can relax, the surface energy is high, the surface tension is high of the original material, then there is a good reason to relax and to reorganize. And materials which have a low surface energy, and polymers, they have, you know, they are large molecules, spaghetti type interactions, yeah. They start out probably with a rather low level of surface energy, and they have not the reason to reorganize. You can, however, do interference patterns, yes, on polymers. It works. But then they are sub-micrometer. Yeah? So we are still trying to understand that, but I think the surface energy is very, very important. There has to be a reason for the material to relax thermodynamically. The kinetics we trigger with non-thermal melting.